Hello. Today we're going to talk about working with collections in C++, in particular with plumbing and the pipes library. To understand the big picture of working with collections in C++, about how that whole world works, let's go back. Let's go back a long way to the beginning of time. At the beginning of time, there was nothing. And then there was 4. That helped us programmers work with collections in various languages, including C++ and C and other languages as well. And that was an era. That was before we realized that STR algorithms were around and were quite a useful thing to use. So then we moved, as a community, to the ST algorithms, and that was an improvement over the for loops, as most people are aware of now. And then we come to that realization, and then now we are collectively moving into modern C++, and the logical next step in C++ after ST algorithms is ranges, right? The popular ranges that we hear a lot about, and that is a great addition to the standard C++. Let's zoom in a little on the transition between ST algorithms and ranges. Let's take a very simple use case for ST algorithms, which consists in applying a function in every element in a collection. So we've got a collection of numbers 1 to 10, and we'd like to apply a lambda function here that multiplies the number by 2. We can do that with the transform. Now, another basic use case for ST algorithm is to filter based on a predicate, and then we'd use CppIf with a predicate like the one here. Now, if we want to do both, as in apply a function only on the element that satisfies a predicate, then we'd need another algorithm, something that would be called like transform if, for example. But the STL doesn't have any transform if algorithm. So if we want to do the equivalent of transform if, then we have to do CppIf and then transform, which is a bit of a problem because it's a lot of code to write and a lot of memory to allocate, and it's just not convenient. With ranges, though, this is extremely convenient. This is a great illustration of using ranges, I think. We've got inputs, and we pipe them in into a range adapter called filter, and we pipe that in a transform adapter that applies a function, right? And this does just what we expect, as in apply the function only on the element that satisfies the predicate. That looks great. We can put the adapters in any way we'd like, and they would be applied in order, which is great. Now, if we take a closer look at this expression, if we take a closer look at what's happening inside of this pipeline, for example, by logging what's going through the transform pipe, the transform adapter, we would expect all the numbers to be printed 1, 2, 3, 4, 5, 6, because we're before the filter, so everything from inputs goes through transform. So we're going to run this little piece of code and see what gets printed out. And we get this. We do get 1, 2, 3, 4, 5, 6, which is expected, except that we get 3 2 times and 6 twice as well, which is a bit surprising, I think. And to be honest, I don't think we can guess what's happening. I don't think we can guess what's happening just by looking at this code. So it's been expected, I think. I certainly stumbled upon that while using ranges on a production use case. So to understand why this is happening, let's see what's happening under the cover. under the covers. So we've got inputs that go through transform, which goes through filter. When we write this, when this statement gets executed, filter gets constructed, and to do that, it iterates all the way to the first element of the range. On the range it adapts, so inputs, pipe, transform, in order to be ready to provide the first element that satisfies the predicate. So to do that, filter calls the predicate on the element coming from transform, which calls the function on 1. And in our case, the outcome is false. So it moves on 1 element and calls up the function on 2, and still not predicate. The predicate is not satisfied, and then moves on 1 more time, and the predicate in the 3 is satisfied. So filter stops here and is ready to be iterated on. Now we start the actual iteration. So we start by reading filter, which calls transform, which calls the function a second time, which is why we see 3 twice. And then filter goes to the next element that satisfies the predicate, so it iterates over whatever comes out of transform. And finally finds one, which is 6, and then it gives access to this value with a second call to f. So this is what we see in the output. Now, most of the time I don't think it's a problem you can observe from the application point of view. I've just observed it a few times. In some cases, it can be a problem if f takes a long time to execute, or if it has side effects. Then maybe you don't want to have to. Maybe you don't want it to be called several times. Now, why is this happening? It's because every element in the pipeline pulls data from the one before it. Right? This is why we've got this behavior. Now, this is the design of ranges. Ranges are great. I think this is a fantastic library, but it has a design. It's not a problem to have a design, but it has a design like everything, which means that it has trade-offs, which means that it does something in a great way and some other things in maybe not as great a way as the other things. The purpose of this talk is to explore another design, right? And this other design is to try and do the reverse, as in a push model, right? Instead of having one element of the pipeline pulling data from the one before, let's try and have every element in the pipeline push something to the one further down in the pipeline. Let's try and do that and see the other trade-offs that we get and the other good things that this brings. And the whole purpose is to use ranges and this push model together to get the best of both worlds. Now, if we take a picture to represent what it looks like to push things further down the line, I think it looks like plumbing, as in really the plumbing that's in the room where you're sitting in, with pipes, with water flowing down the pipes, for example. It's a good example, I think, because you can imagine sending liquids to a pipe, and the pipe pushes that liquid through and over to the next pipe down the pipeline, right? So we can think of it as just pipes. So if we think of it that way, then what's happening is that one goes through the first pipe, comes out with the function applied, and then goes through the filter to make sure that the application of the function satisfies the predicate. And whenever one satisfies the predicate, then it gets pushed over to another place. So it has to come out somewhere. It doesn't go into the void. So let's create a new pipe, like an ending pipe that we call pushback, and we sort of attach to the container like results, which is something like a vector where we can call pushback on. Right, so we send every element in turn to the pipeline, and every pipe pushes whatever comes out to the next pipe down the line. So this is a pipeline. So far, this is just a picture and a vision of the mind. Now, can we write code, actual code to do that? We can. And we can use one library which is called pipes that does just that. And the purpose of this pipes library is to allow you to write code that looks like the drawing, like the pipelines that we see in the picture. This code actually compiles and runs, and you can find it, for example, in this library on this GitHub pipes. Now, if we make the same test as before to make sure of what's going through transform, then we get 1, 2, 3, 4, 5, 6, which is what we expect, what we expected in the beginning. Now, you know that in this pipes library with the pipes metaphor, there is no pipe operator. There's this greater, greater, equal operator, which may sound a bit surprising. So why? Well, when you think about things coming through a pipe, you can think of those things coming with a direction, and then you can think of the equal sign as the pipes, which form the greater equal, which could be a good explanation. But there's another one which is more technical. It's because this operator is right associative. What does that mean, and what does that imply? Well, if something is right associative, if you've got several of them in the same expression, they get passed from the right and then to the left. So when the compiler passes this expression, it would start by associating the ones on the right to create a new object, which let's call it pipeline 1. Then we associate pipeline 1 with transform, and then we have another pipeline. And when we associate the inputs with this new aggregated pipeline, and then we can just iterate over the inputs and send them one by one in the pipeline. This, in this particular example, is an L value, but this could just as well be an R value, and this is the exact same principle. Now, if you have right associativity, it means that we can use R values as inputs just as easily as L values. Now, if we use the pipe operator, which is left associative, we start by combining the elements on the left, right, which output something, right? And this something has to be associated with the rest of the pipeline, right? So this something somehow has to keep track of the inputs, right? A simple way to keep track of the inputs is to have a reference pointing towards the input. Now, having a reference to an L value is okay, but when it's an R value, it's more complicated. It's really more complicated. Now, ranges have this pipe operator. So how do ranges manage to do that? The thing is, when you try to do that with ranges, you get a static assert, which is a very expressive error message, by the way, that tells you that you should not use an R value. So this is just a trade-off. The pipe operator makes using R value more complicated than the greater equal operator. Great. After this introduction of pipes, let's see what pipes can do for us with that push design. So we're going to start with having a look at what a pipe exactly is and what's inside of a pipe, and then we'll see what can get into a pipeline and what can get out of a pipeline and to benefit from the push model. So we've seen transform, we've seen filter, and quite a few others. Now, if we zoom in on one of them, let's say transform, because it's probably one of the most, one of the easiest one to think about. I'm going to show you what's inside of transform by just coding transform from the ground up. So we've got here a piece of code that has nothing, and we are going to implement transform in it. To make sure we implement it correctly, we've got unit tests that does what we would expect with transform. We have an input collection, and we'd like to pipe the input into transform with a function that does something like ×2, and we would expect all of the elements to be multiplied by 2, right? And we compare the result with expected. I'm using catch2 as a testing framework here. Right, so we've got to have this transform somehow. So let's do a transform class. And it has to be constructed with function. So it can be one element. So let's have an explicit constructor. But we'll have a function which can be about anything. So let's use a template type. And we'll just keep the function in with a parameter that we will call function. Right, so now we can construct it. As we will see during the talk, when you have a pipe, you can do a lot of things with it, and it integrates with a lot of things, including existing things from the SCL. So we're just going to tell the library that this is a pipe by inheriting from a specific base class. Now, I'm going to show you the code of that base class. It's not tremendously complicated. This is just that. It's more a tag than anything, but it's implemented as a base class just for the sake of extension purposes, potentially. But it's just a tag, really. Now, the library knows that this is a pipe, so we don't have to do a lot of things. We don't have to implement the operator greater, greater, equal. We don't have to implement integration with anything. We just have to implement what's specific to transform, which is applying a function. So we've got we have to implement a function that's called onReceive that says what to do when transform receives something from the pipe that's before it. So we receive something, let's say a value, that can be about anything. So let's use a template as well. And there's the rest of the pipeline. When transform has to send whatever something its result to the rest of the pipeline. So let's call that tail, for example, tail pipeline. Let's not worry about the type of tail pipeline. Let's just say it's a type. And we can, what we want to do is to apply the function and send the result to the tail pipeline. To do that, the library provides a send function. So it's a free function that's in the namespace pipes, which is in this include. So we're going to send the result of applying function on value to tail pipeline. Right. Okay. Now the library is it's compatible with C++14 because I think it's currently it's a reasonable trade-off between power of the language and what people have in existing potentially legacy code bases. So if we go back to the calling side, we have to pass for example, lambda without specifying a type. In C++17, we're going to have automatic deduction, but in C++14, we have to go back to the good old helper function that will deduce the template for us. transform of a function, and it will return right. Now they can't both have the same name, so we're going to change this name, for example, to transform pi. Right. Let's compile and run. I'm expecting it to fail because it's a live demo. Surprisingly not failing. Let's see, let's wait. It's probably going to fail. Succeeded. And what's the result of the test? Let's see that. All tests passed. Wow. The live demo was successful. That's great. Okay. So, well, anyway, the purpose of this demo was to show you that it's very easy to implement a pipe. This is nearly the actual implementation of the transform pipe. There are just a few details to work out, like, for example, if not having a function, but like not a free function, but a member function or something like that. Maybe you want to do std invoke instead of just calling that way. But these are just details. Essentially, it's really easy to implement a pipe. Right. Now let's see one thing that I think is specific to the push model and to pipes. I haven't seen that anywhere else. It's the concept of branching out. Because if you think of a pipeline as in real life with plumbing, you can imagine a pipeline branching out into several directions. Right, this is something that we can imagine quite easily. Now, let's think about this simple use case of having a T pipe that would do a bit like in Unix in the T program that would dump somewhere the whatever commits way and send it on to the next pipe, right? So we could dump what comes out of transform to this pushback to intermediary results and still send the result onto the filter. If we write this with code, this is what it looks like. We have inputs that goes into transform, that goes into T, that has both an output to pushback and one to filter, and an output to pushback. And what's happening then is that everything that comes out of transform goes down to the intermediary results, and only what satisfies the predicate of filter goes through filter. This is allowed by the push model, right? Because since a pipe is sending to another one further down the line, it might just as well send it to any number of pipes. And T is just an example of true direction, but we can think of sending to any number of pipes with, for example, the fork pipe, right? That would duplicate or triplicate or n-plicate, I guess, your data and send them to other pipelines, which could be any sort of pipeline down the line. I think this is very unique to the push model. The point of that is that once you've transformed your data with F, you don't have to store it to 3 different places with memory allocated for that. You can just pick it up with the fork pipe and send that to 3 different pipelines. And if we transform that into code, the purpose is still to have code that looks as much as possible as the drawing, which is the point of the code below that mimics the drawing above. Another way to branch out is to separate out the elements of a tuple or a pair, right? The UNZIP pipe does just that. If we see that on an example, if you consider a map, which is represented as a collection of pairs, we can unzip those pairs into a separate collection of keys and a separate collection of values with just this line of code. But this was what's inside of a pipe, which are specific to pipes, which are so an easy way to implement them, and the potential, we can potentially branch out. Now, if we think about what gets in a pipeline, how can we benefit from the fact that we're pushing to the pipe? How can that benefit to capturing inputs? Well, so far we've been working with vectors in all the examples that we've seen. Now, there's nothing specific to vector really. We're just iterating over inputs. So anything that has a begin and an end can be iterated on and can work with this pipes library. So that can be any range really. And this is where ranges meet pipes. We can create a range by using range adapters, very powerful range adapters, and pipe the result of that to a pipeline that would potentially branch out, for example, which ranges can't do. Now, there's another thing that we can do to benefit from the push model is to pick up the results of STL algorithms without storing them to a container. Imagine this algorithm, set difference, that takes two sorted collections, and outputs to an output iterator the elements that are in the first collection and that are not in the second collection. If we'd like to do something with those results, for example, applying a function or filtering on them or whatever, normally we'd have to store them into for example, a vector and work on the vector. Now, what if we could somehow make set difference send its results to a pipeline that would avoid the need from having a full container for that? Well, it turns out that we can by taking advantage of the interface of the output iterator, because set difference is sending data to the output iterator, and pipes turn out to have the same interface, or they are compatible with the interface of output iterators. This is one of the things that you get for free by using the pipe base that we've seen in the demo. So you can just stick a pipeline in the position where you would normally put an output iterator, and this pipeline will pick up the results coming out of the algorithm. It gets perhaps even more interesting if an algorithm has several outputs. In the standard library, there are not many algorithms that have several outputs. There's just partition copy. But if we think a bit further than the STL algorithms, the official library, standard library, we can easily imagine algorithms that have several outputs. For example, imagine an algorithm that takes two collections, a bit like set difference, but that would send separately the elements that are in the first one and not in the second one, and the elements that are in the second one but not in the first one, and in a third output, the elements that are in both. A bit like a mix of set difference and set intersection. Let's call that set segregate. It's not the purpose of today to implement set segregate. So let's imagine that we have it. It exists, not in the standard, but this exists in open source projects. So set segregate would have three output iterator that we can branch to three pipelines of any shape and form, and we can build a quite elaborate pipeline with just a few lines of code that again mimic the drawing. So I think this is a great advantage of the push model. Now, if we have several ranges, today, if you want to work with several ranges, I think that the best way is to use ranges with zip. The purpose of the zip is to bring together two collections, right? And it does that by putting the corresponding element into a tuple, right? Or a tuple of two elements in this case. So if we want to zip the collections together and work on this association, for example, by filtering some tuples or applying a function to some tuples, we could do something like that. Now, this is perhaps unnecessarily verbose. We could use C++14 auto in lambda just to hide the long name of the tuple, and we can use C++17 structured bindings to hide listed gets, which looks much more concise. Now, so this is using tuple, and the consequence is that we don't see the arguments separately in the interface, and we still have to extract them from the tuple even if we're using structured bindings, right? Now, if we think of the push model is just like we saw, it's calling send. So it's like applying functions. And when you're applying functions, you can have as many arguments as you'd like without having to use a tuple. As opposed to pooling data, you can just pull one piece of data at a time. So you have to group that in a tuple, I think. Right, so let's imagine this mux pipe that would accept two collections, and it would somehow absorb them and send them to the pipeline in code that would look like that. So we have mux that associates two or any number, for that matter, collections, and would send those collections simultaneously to the pipeline, right? And the advantage is that the prototype of the function inside a filter has int A, int B explicitly. It's not a tuple. Can we do that? Let's see that. Let's go back to the code. Let's try and implement mux with transform. Well, in fact, mux is, we're going to make transform compatible with mux. Let's not implement mux. Mux is a bit more code to implement. We're not going to get into that now, but let's make transform compatible with mux. So we've got this second unit test that has two collections, this one and this one, and would mux them together and apply a function on every pair of elements, right, and collect the results in a collection, right? So we would expect the sum of all corresponding elements, so 1 plus 10, 2 plus 20, etc. If I run the program, I've got a build failure because our transform only accepts one value, right? And mux is trying to send several values to transform. So we have to change transform to make it accept several values. Let's just do that. We're going to add the ... dots and some rules on the names. So we have to have a function that takes several arguments. And I think that's about it. Let's, oh yeah, there's missing S here. Let's compile and run the program. It's building the full test suite of the project. Yeah, it's passed. So we've made transform compatible with mux, and we've made this example compile and work. So there's no tuple here. Now let's see a concrete example with a domain which I find fascinating, even though I don't know anything about it. It's biology, right? So we're going to see a small example in biology. I'm going to walk you through it, but it's you don't need to have any knowledge. I don't have any. Right, so it's about DNA. So this is the DNA of somebody. Let's call that person John. The way that works, those are John's chromosomes, so they're present in every one of John's cells. There's one that's coming from John's dad and one that's coming from John's mum for every pair of those chromosomes. Now, when to create new chromosomes for John's kids that are new individuals that don't look like John or dad or John's dad or John's mum, they're not like clones. It's like a new set of DNA. There's this absolutely jaw-dropping, mind-blowing phenomenon that's called the crossing over. That consists in bending chromosomes around one another and sort of break them in order to pick either a gene from John's dad or from John's mom, or either a gene or like a set of nucleotides or like a bit of DNA. So what it does is that for every corresponding pair from the two chromosomes, it either keeps them in the same order or swap them around, right? And it does that repeatedly for every pair of DNA chunk. Now, let's try and code that, right? Let's try and represent that with code. Let's say that we're working in bioinformatics or something like that, informatics. How would we do that? Well, if we do that with pipes, how would we do that? Well, we need to associate the two chromosomes. So we think of MUX. And then we've got, so MUX is going to provide every pair of chromosomes. And we say that we either want to leave them the way they are or to swap them around. So we're going to pipe them to this transform function that would either leave them the way they are or swap them around. And then we can pipe the result to UNZIP in order to break them apart and have two chromosomes for two potential kids. The function to do that would be either to leave them the way they are or swap them around randomly. Let's assume we've got a random number generator. And that's about it. Now, if we test that program, if we represent a chromosome with strings and genes with characters, with D coming from dad and M coming from mom, and we are producing two chromosomes, so two set of genes, we can just MUX and transform them UNZIP, and that's it. And we can print them out. If we test that program on one run, it gave that. Right, so this is a sort of simulation of a crossing over in a declarative way, character way, yeah. MUX is one way to associate collections together. If we, just for the sake of the example, we directly print out the results through the cout stream, for example, with those pipes, it lets us experiment with other pipes. So other than MUX, we can combine the two collections to create all possible combinations between the two collections, right, with Cartesian products, and still using no tuple. Or we can create all the combination between two elements of the same collection. Or we could iterate over a collection by taking the elements 2 by 2, like 1, 2, then 3, 4, then 1, 2, then 2, 3, then 3, 4, with this adjacent pipe, which is horrible to write with a for loop, and still no tuple. So this is what can come in a pipeline, and the main point I think is that the two main points I think is that we can pick up results from ST algorithms such as set difference, and also that we don't have to use tuples to manipulate several input ranges. Now let's see what can come out of the pipeline, because as we've seen so far, we have a sort of ending pipe, right? Like pushback, for example. Pushback is extremely simple. It's just called pushback on the container it's attached to, and passes anything that comes its way. Now, the thing is, pushback is at a location where we can write code. So pushback is simple, but what if we could write something more elaborate, right? To, for example, handle complex integrations into containers. So we've got pushback, which is the equivalent of back inserter, but we also have insert, which is sort of the equivalent of inserter, and override, which is the equivalent of std begin. Now, if you consider insert, it's sort of the equivalent of std inserter, because std inserter is a bit weird because it forces you to pass the position where you'd like to insert data in. So if you'd like to insert in a vector, for example, that makes sense. But if you'd like to insert into a sorted collection, for example, a set, then it doesn't make sense to tell the set where you want to insert, because it's the set that will choose it. That's its job to make sure that it inserts at the right position. I mean, you could give it a hint, but if you don't have a hint, and typically when using an output iterator, we don't have hints, it doesn't really make sense to write something. So we write end, and perhaps it's a pessimization, or perhaps it doesn't have any impact, but it certainly has an impact on the code that we write, because we have to write that and read that, and that just doesn't make sense. So we can just use pipes insert that just does the right thing. It accepts the hints, but it does the right thing if you don't pass a hint. Now, if you, for some reason, want to ignore what comes to a pipe, you can use dev null. So imagine we'd like to truncate the pipeline and for some reason ignore the second output of set segregate, but still benefit from the first two ones. We could just use dev null as in the code below. And so we've seen pushback to insert in a vector, but imagine that you don't have a vector, but you have a legacy collection. It would be a shame not to use the STL or ranges or pipes or any modern alternative to work on collection, just because your destination is some legacy code that doesn't have a nice interface of pushback, for example. Or to work around that, you can just do anything at the end of the pipeline with for each. So for each takes a function and applies that and passes what comes its way to that function. So perhaps do my custom treatment consists in inserting data to, for example, a legacy collection, which lets you have some part of your code that's modern, even though some of it is still legacy. Now, if you consider a map now, let's take this example of this map, which has 3 entries, and let's consider a second map, which has some entries that have a key that's already present in the first map, but also keys that are not present in the first map and the other way around. And let's say that we would like to insert the new entries into my map. With the STL, it's like all or nothing for the keys that are already in my map. For example, if you'd like to insert 2 and B2, if there's already 2 and B1, you can either ignore B2 and keep with B1, or you can replace B1 with B2. But there's no way, there's no middle ground. You can't aggregate B1 and B2, even though that's often what we'd like to do. So in this case, for example, let's say we'd like to aggregate the strings, to concatenate the strings, and we'd like to have 2 and B1, B2, for example. We can use this ending pipe, which is map aggregator, that does just that. So you pass it to destination and a way to aggregate values if keys match. In our example, the values to aggregate are just strings. So it consists in adding them. So we can just use std plus, for example. If you compare that with writing that manually with the for loop, for example, this is much shorter and arguably more expressive if you know what map aggregator is, obviously, because it's not standard. I think this also comes from the push model, because there's a position in the pipeline to pick up the result that come from the rest of the pipeline and to do something with them before inserting them into their final destination, like a map. We've seen quite a few strengths of the push model and the pipes library in particular, but that wouldn't be fair if we didn't see some of its limitations, because pipes and the push model have a design just like everything else, which means that they have trade-offs, which mean that there are things that they do well and things they don't do as well. For one thing, pipes don't know what's coming next. In our code, if you remember, go back to the code, in our implementation of transform, we've got this value coming in on receive, but you just know what's coming in right now, and you don't know what's coming next, or if anything is going to come after that. So this makes it more difficult to implement reverse, for example, because if you want to reverse, you don't know when you're finished in order to reverse, or drop last, which consists in not pushing the last elements because you don't know when this is the last. I mean, I don't know how to implement those two functions with pipes. Perhaps it's possible, but I haven't found how, because of the push model. And pipes don't cache input data. I'm not sure this is a limitation of the push model. It's certainly a limitation of pipes, of the pipes library, because since anything can come into a pipe, it's a template, we can't store it because we don't know what type it is, right? So how can we implement split? As in, like, if you have a string and you like to split it according to the commas, for example, or spaces. I don't know how to do that with pipes, even though we can do that with ranges, and we can also do reverse and drop last with ranges. When we build a pipeline, we can build it bit by bit, right? We can build a chunk of the pipeline and then associate it with another chunk, and then tack on the end of the pipeline and keep that for a while, and then later send the inputs. But when we send the inputs, it has to be a whole pipeline, because when you send the inputs, they're not going to be cached into the pipes, they're just going to flow through. So the pipeline has to end, right? The inputs are not going to end in the void. I mean, it can end with dev-null, but it has to end with something. So you can't have a partial expression with just the inputs and a subpart of the pipeline. And as you saw in all the examples, we have to create the result beforehand, unless you're piping to a stream like cout, for example. But if you're piping to a pushback, then it has to push back to something, right? I mean, it could be an R value, but I don't think that there's a lot of purpose to send data to a temporary value that's going to be destroyed just after that. So it makes more sense, I think, to have an end value which is created beforehand, right? So as opposed to ranges that can create the outputs and the pipeline in the same expression, with pipes, you have to have two expressions. I mean, you have to have all the containers created beforehand, all the results. Now, those trade-offs allow to have the strengths we've seen. We started with seeing that transform calls only one. I mean, it's called only once. The function inside the transform is called only once per element, which is what we expect. We can use R values as inputs. We can branch out in two directions with T, or in any direction with fork. There's a typo here. Fork used to be called dmax, so you should read fork here. Or you can break down a tuple with UNZIP. We can pick up whatever comes out of a nested algorithm, such as with the example with set difference, we can have multiple inputs values without using tuples. We have an entry point towards the end of the pipeline where we integrate with the destination, which allows us to do elaborate treatments such as map aggregator, and are very easy to implement. Now, if you would like to implement one, because yeah, they are easy to implement, and quite a few people have already implemented some pipes, and I'm very grateful for that. You're welcome to contribute to the library by sending a PR or opening an issue in this GitHub repo. And actually, you can contribute right now by answering a question. Imagine we've got this sort of pipeline, right? Input goes to transform, which goes to something like pushback, for example, and R, the result would be a vector that has a pushback method, or R could be a set, for example, that has an insert method. What do you think of allowing this kind of expression, right, without specifying pushback or insert? Just do the right thing. If it has pushback, the pushback. If it doesn't have pushback but it has insert, do insert. Even though that wouldn't replace the first expression, the first set of expression, but both would be allowed. What do you think? Is that a good idea or not? I mean, obviously, I can't ask you. I can't see your hands rising in front of your computer, but perhaps you can just answer in the Q&A session and or upvote a question that, a card in the Q&A that has an answer that you would agree with. And the final question is, how should we call this greater equal operator? Because greater equal is not such a cool name. So what would you like to call it in the context of a pipeline? That's it for the presentation of pipes and the push model. We'll be happy now to take your questions with the Q&A. We've got a question here. Is the pipes library robust and ready for use in production codes? Well, to the best of my knowledge, it is. I know some people do use it already. It has a fairly strong set of tests, as you can see in the GitHub repo, and I've used part of it in my own production code as well. So I say you can have a go ahead. Yeah. Now that said, it's still. I mean, it can still evolve, right? I think it's a fairly new concept. I mean, at least for me, it's fairly new. It's just been a few years, a couple of years I've been working on that. So I'm still welcoming suggestions to make it evolve so it can change. Is pipes allowed to be lazy also? Let me think, what do you mean by lazy? Because, I mean, pipes don't cache data. They would process everything that comes their way. So I'm not sure that would make sense in that particular model, unless I'm missing anything. How efficient is the pipes library? Does it make copies of inputs? If my input is a vector of a complicated class and my function is CPU intensive, how does the performance compare? Well, to compare, I think it's fair to compare with ST algorithms and ranges for the features that have in common, for example, transform and filter. I had made such comparisons in the past, and they were in the same ballpark. It depended on the use cases, but sometimes there would be ranges that would be faster, sometimes pipe that would be faster, sometimes the STR algorithms will be faster. But the fact that pipes is never calling the transform function several times certainly helps. And also the fact that it doesn't have to allocate intermediary collections to work on the intermediary results also helps as well. What are some advantages of the pull model in ranges versus the push model in pipes? Anything of that? Yeah, well, some advantages of the pull model correspond to the limitation I've mentioned of the push model. For example, with a range, you know when it ends, so you have more control and you can do more things like reverse and drop last, for example. Also, one thing I haven't mentioned, now that you make me think of it, is if you want to implement the equivalent of algorithm that takes several inputs. Let's take an example. Imagine set difference. I always come back to set difference because it's my favorite algorithm. But imagine set difference, right? If you'd like to model set difference as a component in a pipeline, well, if you do that with ranges, you can have some sort of like range adapter that takes two input ranges, and when you read that adapter, it would give you the next element that would come out of set difference, right? And this is something that actually exists in the ranges in the range v-tree library. Now, if you think about how to implement that with pipes, this is way more difficult because it would mean that you have two pipes joining somehow, right? And this is not specific to set difference. In the general case where you'd like to have two pipes or two pipelines somehow joining and then potentially breaking out again or joining back again, then I don't know how to do that. I mean, in a simple way. I mean, I wouldn't. I've thought about that because this question has already been brought up with pipes, but I wouldn't know how to write it in terms of syntax, in terms of client code using the pipes library. How would you write pipes that join together? I don't know, and I consider that a limitation, even though I haven't come across any production use case that would need that. Does it support parallel execution? Well, it depends on what sort of use case. I think one great use case that the library does not support now is with the fork pipe. I would love to see the fork pipe spin up perhaps a new thread for each of its outputs, so that every branch coming out of the fork pipe would run in parallel with, for example, a task. But I haven't implemented it. I'm not sure how to implement it, to be honest, and I would welcome contributions in that direction. How does pipe push model compare to other libraries that implement this style, like RxCpp, the reactive extensions to C++? Well, I'm not an expert in RxCpp. I certainly looked it up to see how it compared with pipes. My understanding is that one thing that they have in common is that they use a push model, like you're suggesting. But one thing that's different is that pipe break out into several directions. The pipes project started as an experiment for the push model and everything you've seen in that talk. It's I mean, some of the things you saw in that talk are not present in RxCpp, to the best of my knowledge. and the other way around. I mean, I'm not an expert in RxCpp, but I'm sure that RxCpp does a lot more things than pipes. I mean, RxCpp, as far as I understand, is more oriented around handling events as opposed to values in a collection. I think that the purpose is not the same. I think that's more like a theoretical difference, but in a concrete difference, you've got different use cases. Okay, that was our last question. Thank you so much for being here. Bye-bye.